Welcome to the course on power quality. Today we will like to cover the topic of analysis and design of 3-phase 4-wire shunt compensator. In the last lecture we covered 3-phase 3-wire passive shunt compensator. So, today we will like to have 4-wire compensator. We will like to first have analysis design of this shunt compensator for 4-wire system for power factor correction. So, the unbalanced 4-wire load shown here in figure A is fed from the balanced 3-phase where the per phase voltage is V equal to Vp, Vb equal to A square Vp and Vc equal to A Vp, where Vp is the RMS voltage per phase and A is the operator for the 120 degree phase shift e to power j 2 pi by 3, which is can be in rectangular code can be written as a minus half plus j root 3 by 2. Well, this is the network. Like you can see the 3-phase 4-wire system with unbalanced load on A phase, B phase and C phase, which is here Z A, Z B, Z C, and connected to the neutral of this load, because it is a 4-wire system, to the neutral of supply system. Well, to compensate this load, unbalanced load, unbalanced non-unity power factor loads of 3-phase 4-wire, we have to have a two set of compensator. One set is connected in star, which you see with the star connection, as known as your notation with the star connection with the notation of By, and the another set of compensator which is here delta connected across the 3 terminals of the point of common coupling, which written as a with the notation of B D with the different notation. So, this network like with this 6 element of compensator can be can be compensated for balance unity power factor load at the supply system, and which can be just represented as equivalent to a source impedance on per phase basis, which is equivalent to a star. You can call it the 3-phase 4-wire star connection and per phase basis with the neutral line to neutral, and the equivalent conductance after power factor correction and load balancing, and it can be converted to like a GY. And of course, if you want to have in place of power factor correction you want voltage regulation, then you can take another compensator of JV BCV, which is responsible for voltage regulating the load terminal equal to the supply voltage like. So, this is the network. Now, this network we have to find out these compensating all 6 elements for different conditions. So, we will like to discuss the analysis of this and find out the value of that is what we call it the design like. Well, now the load current in terms of load admittance can be expressed as follows. A phase current IA can be written as a GA plus JGB into Vp, that is a load, you can call it the admittance multiplied the phase voltage. Similarly, for B phase GB plus JBB A square Vp, that is virtually for 240 degree phase shift of the voltage for B phase, and C phase current can be represented again GC plus JBC and with the operator of 120 degree A into Vp. Well, these are the 3 phase currents. These can be unbalanced reactive current or non-unity power factor current, but we are considering here of course typically the sinusoidal balanced supply voltage. Well, the symmetrical component of these line current of unbalanced 4-wire load are as follows, which can be written as a 0 sequence current plus equal to IA plus IB plus IC by root 3, and this I1 positive sequence current can be written of the load current IA plus A IB plus A square IC divided by root 3, and I2 negative sequence current can be written as IA plus A square IB plus A IC divided by root 3. Well, these if you put the value of from equation 35 of IA, IB, IC in the equation of positive sequence current of 0 sequence current of I0 and positive sequence current I1 and I2. So, I0 can be written directly GA plus A square GB plus A GC from above relation, and plus J BA plus A square BB plus A BB with the closed parenthesis into Vp by root 3. Similarly, I1 can be written equal to GA plus GB plus GC plus J BB plus BC divided into root 3 Vp by root 3. okay, and I 2 can be written G A plus A square G B plus A G C plus J B B A plus A square A B B plus A square B B B C and V P by root 3. So, these are the three symmetrical component of the load current, okay, positive 0 sequence, positive sequence current, negative. Similarly, 0 positive and negative sequence symmetrical component of the line current of star connected compensator are as follows. IOCY equal to typically in terms of again compensator current of IACY plus IBCY plus ICCY divided by root 3. And we can keep the value of these compensators because compensators are lossless, that is why it is represented only the your susceptances. So, it can be J can be taken out. So, it will be ACY plus A square BCY plus A BCCY with the Vp divided by root 3. Similarly, positive sequence current of this your star connected compensator can be equal to C denotes here for compensator. So, it can be IACY plus IBCY plus A square ICY divided by root 3, which can be equated equal to J into VACY plus VBCY plus VCCY into Vp by root 3, and I2CY can be written again in the similar manner IACY plus I square ICBCY plus A CCY by root 3, and which can be equated in terms of parameter equal to J BACY and A BCY plus A square BCCY into Vp by root 3. Well, similarly, the 0 sequence, positive sequence and negative sequence symmetrical component of the line current of delta connected compensator can be also written as follows. So, I0 CD means 0 sequence current of the delta connected compensator can be written as IACD plus IBCD plus ICD divided by root 3 equal to 0, because there is no connection of delta connection to the neutral. So, certainly 0 sequence current from the delta compensator cannot flow, and then positive sequence current I1 CD equal to IACD plus A square IBCD plus A square ICCD divided by root 3, and it can be written in the again lossless component which are shown in the circuit J VABCD VBCCD plus VCACD into Vp by root 3, and I2CD equal to IACD AICD plus AI square ICCD divided by root 3, and you can keep the value of typically of this current in some of the your susceptances. So, J can be taken out, and in bracket A square B ABCD plus BBCCD and plus A CCD into Vp by root 3. So, well, with the use of 6 element lossless compensator, 3 connected in star and other 3 connected in delta configuration across the load, negative and 0 sequence component of load current are to be eliminated, and the power factor at the load bus is to be improved to unity, and it results in a sinusoidal unity power factor supply current. So, for this purpose it must satisfy the following condition. The first condition is sum of the real parts of negative sequence component of load current and compensator current must be 0. Means the negative sequence component of your load current should be compensated by negative sequence current of real part of the both the compensator. So, real I2, that is load negative sequence current real component plus the star connected compensator real I2CY and real part of this I2CD so must be equal to 0. So, that is the one condition, and we can keep the value of this. This is the value after keeping all these load conductance, load susceptances and the typically susceptances of the, you can call it the star compensator and delta connected compensator, because they have only the susceptances, they do not have really conductances because it is a lossless compensators like So, real part should be equal to 0. So, we get this equation, one equation from here, and you can eliminate the voltage term from both the sides. So, it becomes simplified equation. Similarly, the second condition is the sum of the imaginary part of negative sequence current of load current and compensator currents must be 0. So, similarly, we can have imaginary part of I2 of load current plus imaginary part of star connected compensator I2CY plus imaginary component of your delta connected compensator I2CD equal to 0. So, we get the again we can put the value of I2 and I2CY and I2CD into it, and then imaginary part of it can be made equal to 0. So, that is another condition we get it, and the another condition is the sum of real part of 0 sequence component of load current and compensator current must be 0. In this case, delta connected elements of the compensator do not contribute, as there is no flow of the 0 sequence current in the delta connected network. So, this condition results in an equation as follows. real part of I 0, that is the load current 0 sequence current, plus real part of I O C y, that is a star connected compensator, which can have a typically the you can call it 0 sequence current, because it is connected in star with the neutral, and this should be 0. Since there is no connection of the delta network with the delta compensator with the neutral, so that term will not be there in that case. So, that is another condition, and you can keep the value of this, and you can get the equation between load, you can call it the admittances, and the star connected susceptances. The fourth condition, of course, the sum of imaginary part of 0 sequence current of load current and compensator current must be 0. In this case also, the delta connected elements of the compensator do not contribute, and there is no flow of 0 sequence current in delta connected network of the compensator. So, this condition results in an equation, again imaginary part of I 0, that is load current 0 sequence current, plus I imaginary, that is imaginary part of your star connected compensator I O C y must be equal to 0, and we keep the value of these two currents in terms of the voltage, I mean the phase voltage, and the parameters of the load like conductance of the load and typically susceptance of the load, and then the star connected compensator. So, we get this fourth condition. There is another fifth condition. For unity power factor at Massey means imaginary part of positive sequence component of load current and compensator currents must cancel each other. The imaginary part of I 1 plus your imaginary part of I C 1, that is star connected compensator positive sequence current, and imaginary part of I C D delta connected compensator, you can call it the imaginary part, they must be 0, and you can keep the value of this in terms of load conductance, load susceptances, plus the star connected susceptances as well as the delta connected compensator. So, you get another equation. Well, these 5 conditions have an infinite solution, because there are 6 unknown susceptances of 3 susceptances of star connected compensator and 3 susceptances of your delta connected compensator, and we have only the 5 equations. So, additional condition together with the above 5 equations may offer a unique solution, means you can get a solution, definite solution like. So, for this purpose the 6 condition have to be added here, I mean typically then only you can get the solution of the design. So, an example, I mean here we like to include couple of examples, and but you may have a many such other conditions also. An additional one condition may be that the imaginary part of the positive sequence component of load current is eliminated by the star connected part of the compensator alone. So, delta connected part of compensator does not generate imaginary part of the positive sequence current. So, hence the first condition is considered for the imaginary part of the positive sequence component of load current is eliminated by star connected the compensator alone. In this case, sixth condition is the imaginary part of, you can call it the your positive sequence delta connected compensator I 1 C D should be, that is equal to, let us say imaginary, you can keep the value of this j in terms of susceptances B A B C D plus B B C D plus B C A C D V P divided by root 3, that should be equal to, this give a condition your all 3 susceptances, sum of all 3 susceptances of delta connected network should be equal to 0. So, this is the sixth condition, and we already have a 5 condition. So, the solution of 6th equation, I mean which already mentioned the 5 condition, and this 6th condition give the susceptances of your star connected part and delta connected part of the compensator in terms of conductance and susceptances of the 4 wire load, and these values are the all 6 compensator elements in terms of the load conductance and load susceptances. So, you get the design for this particular solution, and you can call it these 6 lossless passive element connected in star and delta configuration across the 4 wire load are expected to result in unity power factor balance supply current like. So, that is the one solution you can call it with the 6th condition added. Similarly, we can have another solution may be achieved by considering that the imaginary part of the positive sequence component of load current is eliminated by delta connected part of compensator alone. So, it results on 6 different solution, as any one of the element of 6 may be 0. Hence, one of the such case is given in which the first element BIC is considered 0, it gives the following design equation. So, we consider the susceptances of A phase star connected network is 0. So, it gives the following design of the compensator for all elements of compensator in terms of load susceptances and load conductances. So, that is another solution of value of 5 elements. So, similarly, other 5 solution may be achieved by considering any one of the 5 elements of the compensator to be 0. So, you will have certainly in that manner typically the 6 solution like or so. Well, the after the compensation by any one condition you find the parameters of equivalent balanced star connected unity power factor load are as follows. The conductance in equivalent load balanced unity power factor load after the putting the compensator you will get a G y equal to 1 upon R y equal to G A plus G B G C plus G B by 3 and the total active power consumed by the load is as P equal to 3 P V P square G y, because V P is the per phase voltage and G y is the per phase conductance, and you can just put this equal to 3 V P square by R y. So, that is the power consumed by the total load, maybe unbalanced load or even it can be single phase load or 2 phase load. So, all conditions of 3 phase 4 wire can be covered under these solutions like. So, well, so we have to extend this solution like a analysis design of the shunt compensator for 0 voltage regulation, because in previous section we consider it typically for unity power factor condition. So, for 0 voltage regulation to maintain the load terminal voltage to be the same as the AC means for 0 voltage regulation, another balanced star connected compensator may be used at the load end. So, after this the entire 4 wire network with 6 compensator, which we can get a unique solution, which already we discussed it, that can be have a balanced star connected per phase load with the source impedance and G y, which we discussed in previous section. And now, because that was for unity power factor operation, now we want to get for voltage regulation. So, we have to put another typically compensating element for all the 3 phases. It is given a unique solution for per phase here. So, we have to put another compensator for voltage regulation J, B, C, V in parallel to the load of unity power factor balanced load like, and we have to find out this value of the PCV in addition to all 6 element value which we already calculated like. So, the additional susceptances of the compensator BCY for 0 voltage regulation at the load terminal is estimated as follows. The load terminal voltage must be the same as the AC terminal supply voltage, mains voltage. So, Vs magnitude equal to VL, and you can put the value of the typically here the VL. So, is the total, you can call it the current, the net current at the source side Vs divided by Rs plus Js source impedance plus the load impedance 1 upon G y plus J B C V, including the compensator impedance in parallel with the conductance of the unity power factor load. So, this is the current multiplied the your impedance of the your total load along with the compensator 1 upon G y plus G B C V. So, solving the above equation, the total susceptance of the compensator B T can be calculated in a manner that B C V equal to X S source impedance plus minus under root X square into A in bracket 2 R S G y plus A square G y bracket close divided by A, where A is a R S square plus X S square typically from the source impedance. By connecting 3 equal valued of susceptances of the compensator of the each value of BCV in star connection across the equivalent star connected load terminals, load terminal voltage is maintained same as the AC source voltage, resulting in 0 voltage regulation like. So, we already discussed the basic formulation in the previous class, the derivations, that how this compensation for power factor and typically in case or voltage regulation in case of single phase, and in 3 phase 3 wire system we have included the load balancing also, because in 3 wire system the load can be unbalanced along with the reactive power requirement. And of course, we discussed even in single phase the reactive power compensation of the load AC single phase load can be either for power factor correction or voltage regulation. These 2 conditions cannot be met simultaneously. So, you have to consider only one condition out of 2, but in 3 wire system then we can have it even the load balancing also along with these 2 conditions. When we come to like a 3 phase 4 wire system, because of load unbalancing on 3 phase 4 wire system, because load can be connected between single phase and neutral. So, you might have a only single phase load connected between line to neutral, or maybe 2 phase between again another line to neutral, and 3rd phase also between 3rd phase and neutral. So, even if you have a single phase load or 2 phase load, maybe unbalanced load of 3 phase, you will certainly have a numeric this neutral current. So, we certainly can have it in 3 phase 4 wire, which we discuss in basically mathematical formulation, that we can eliminate the neutral current also. So, any unbalanced load, I mean in 3 phase 4 wire or 3 phase 3 wire can be realized as a balanced load, as a unity power factor load by this lossless passive element. I mean we all the time discuss that we should use the lossless passive element, in the sense that we should be able to use only the inductor and capacitors for providing the function of reactive power as well as load balancing and neutral current elimination. So, today we will like to discuss the numerical examples to demonstrate all these features which we developed the mathematical formulation with proper circuit in the previous part of the lecture like. So, let us come to the typically the first numerical examples, which is on the power factor correction of single phase like. So, if you look into the problem, it is a single phase having a load having the load impedance of 5.0 plus j 3.0 per unit. It is fed from an AC supply with the input voltage of 230 volt 50 hertz and a base impedance of 5.2 ohm, and it is realized as a unity power factor load on the supply system using a shunt connected lossless passive element, may be the inductor or capacitor as shown in the figure, and calculate the value of compensator element. Again it can be, if it is a capacitor, it will be in farad or microfarad, or if it is a inductance, it can be in Henry or millihenry. And then after compensation, what is the equivalent resistance of the compensated load, because it is to be compensated to unity power factor load after this. You can call it like a typically the combination of both, as you can see here in the typically in the waveform like or so. So, well, coming to the solution of this problem, in the next slide. So, we can say there is of course supply voltage given in the numerical problem 230 volt and frequency is 50 hertz, and we have a single phase load of again 5.0 and 3.0 per unit with the base impedance of 5.2 ohm per phase. So, we can calculate the actual value because it is given in per unit. In of course, in power system we are or even like a electric power system, we consider always the per unit system. So, you must have an idea of per unit system. So, certainly to get actual value we have to multiply it by base impedance. So, if it is like a 5 typically ohm, so it had to be multiplied by base impedance. So, then you will get actual ohmic value of the load, like a resistance is 26 ohm and load reactance which is again 3 ohm multiplied the base impedance of 5.2, it comes to 15.6 ohm. So, load impedance in terms of ohm now becomes like your 26 plus j 15.6 ohm, and 26 is the resistance and 15.6 is the reactance of the load, and you can convert this your rectangular coordinate impedance into the polar coordinate, means 30.321 ohm at the angle of 30.964 degree. So, that is the load impedance we have. Now, this load impedance which is connected to the source, we have to now calculate the compensating element in shunt of with that. So, that power factor correction is made unity, and typically you can call it it's behave like a resistive load. So, load current before the compensation we can call it V upon ZL, and that is 230 upon 30.06. So, at the angle, because ZL has an angle, so when it will go the angle above, it will become minus angle. So, you will have a current typically 7.586 at the angle of minus 30.964 degree ampere like. So, out of that we can find out the reactive current, that will be Is sold into sin theta, or it can be Is sold XL upon ZL, and this will come like 3.903 ampere, where theta is the power factor angle of the load which is given in the impedance also. The compensating capacitor now should supply the same reactive power of the load, hence IC, that is a compensating current should be equal to reactive current of the load, that is 3.903 ampere. So, value of the capacitor for power factor correction, because it is a because load is inductive, so the compensator should be capacitive. So, it will be C equal to IC upon virtually the V omega, because omega C equal to you can call it like V omega C equal to IC. So, C you can calculate from IC upon V omega. So, we can keep the value of this like let us say IC 3.903 divided by omega here for 50 hertz is 2 pi f, that is 314 into 240. So, it comes like a 54.106 microfarad like So, that is the if that much capacitor we connect in parallel, then certainly we get a unity power factor load. Now, we can find out what is the supply current after the compensation. that will be IS new, IS old into cos theta, that is only now the resistive circuit IS old RL upon ZL, and that is equal to IA 6.05 ohm, and equivalent resistance of the compensated load. Now, we can say R equivalent V upon IS new, that is 230 divided by 6.505. So, the equivalent load resistance will be 35.357 ohm. So, that is the solution of this typical numerical problem. And it is a simple power factor correction problem by using the compensator or capacitor in parallel with the your inductive load. Now, coming to second problem, again on the single phase. Here a single phase AC supply has a AC mains voltage of 220 at 50 hertz. The feeder, here we have considered the feeder ohm impedance of 3 ohm inductive reactance, after which a single phase load is connected, 12.9 J9 ohms is connected. I mean, we have connected here the consider the source impedance. It may be a, you can call it like a impedance, leakage impedance of the even your transformer. I mean, short circuit impedance of the transformer, which is highly inductive, and you can have a feeder inductance. So, we for simplicity at the moment we have considered that there is a some impedance which includes the distribution system impedance, and it is only the inductive one of 3 ohm. So, calculate the voltage drop across the source impedance, the voltage across the load. If shunt compensator consisting of passive lossless element, either inductor or capacitor, is used to raise the voltage at the same as the input voltage, to calculate the value of compensator element either in farad or Henry and its kVA rating, and the voltage drop across the source impedance after the compensation. So, this is typically a voltage regulation problem. I mean, you might have seen now we can connect this compensator. If you look into here, this compensator we are connecting in parallel to the load. Now, very purpose compared to previous problem we consider the power factor correction. Here we are considering the voltage regulation. So, now we have to find out the shunt compensator value for voltage regulation. Certainly, its value will be little larger than the power factor correction. The reason being that we have to take care of the drop of this source impedance also. Well, of course, you can see here, I mean, we put the value, of course, we made a this waveform for these actual data, and you can see the this current, I mean, the source current is slightly leading than the voltage. So, even the you can call it 0 voltage regulation, means whatever is the source voltage should be equal to the load voltage, that will come always little leading power factor, because your source impedance is of inductive nature, and that is the reason you can just see all the parameters here. However, the compensator is capacitive, so this current is typically 90 degree leading than the voltage. I mean, the load is certainly it is a inductive, so it is lagging than the voltage. So, all these waveform can give you typically the concept of, I mean, how this compensator will work like, I mean, also. Now, coming to the numerical problems of this, I mean, given the supply voltage of 220 volt, frequency of 50 hertz, and single phase load of your 12 ohm plus 9 ohm, and the source impedance here is your ZS equal to RS plus JX, that is only RS is 0, and we took only the inductive source impedance, that is 3 ohm for the case of simplicity to understand, and the load impedance here is 12 plus I mean J9, that comes the impedance as a 15 ohm. So, you can find out the total impedance, that is ZS plus ZL, and you can add in that typically of J3 only in that. So, it becomes 12 plus J12, the total impedance of the circuit including the source impedance, and the value comes around 16.97. So, now the load current before the compensation, that is we call it as IS old, supply old current before the compensation, Vs upon ZT, total impedance of the circuit, 220 divided by the 16.697, that comes 12.96 ampere, and the voltage across the source impedance now will be IS old into ZS, and that you can call it 12.96 into your 3 ohm inductive. So, 3 into that will be your 38.89. So, that is the voltage across the source impedance, and the voltage across the load we can find out from IS old into ZL. So, it in place of it is 194.45 because of the source impedance. So, in place of 220 we are getting the voltage across the load only 194.45. So, that is the remaining voltage, the drop across the source impedance. So, that is typically. Now, let us come to the typically the another part for calculating the compensation. You can call it the compensation rating, compensator rating, I mean, which I have to keep in parallel with the load to maintain the voltage regulation. So, now we can go load admittance, I mean, that is we have to keep in terms of admittance GL upon JBL 1 upon ZL, and you can get the value of typically of admittance 0.0533 minus J 0.0400 moho, because the admittancy will be always in moho, and the load power factor can be made typically unity by connecting the susceptance of this compensator for typically for power factor correction. So, it will be minus BL, that is around 0.04, because that is the value of typically of you can call it the load reactive part impedance. So, let the susceptance of the value BT in moho is to be connected in parallel to the load to raise the load voltage equal to the input voltage VL equal to Vs. So, BT has two components, one for power factor correction and other is to raise the load voltage equal to the input voltage. Hence, the BT will be equal to BPF, which we have already got it for power factor correction, putting a like you can call it like a lossless element in parallel with the load for power factor. Another is the BCV, that is for regulating the constant voltage across the load. So, basic equation to regulate the load voltage equal to the input voltage is this we derive already, that you can call it the voltage across the load, which is the calculated value here equal to should be the source voltage. And how we calculated this? Typically the load voltage we have calculated Vs, we got the load current, the total current of the circuit multiplied the load admittance and load impedance you can call it. So, this we got typically the voltage across the load, that should be the magnitude of this should be equal to the source voltage, and solving this equation we got the BCV, that is the typically you can call it the voltage compensator susceptance. It should be XS plus minus under root XS square minus XS square RS square in bracket 2S GL plus RS square GL square and XS square GL square divided by XS square RS square. So, we can substitute the value of XS equal to 3 and RS equal to 0, then the equation becomes simplified and GL equal to 0.0533, and considering the minus sign in your plus minus for lower value of compensator value, because lower value will only give the lower typically with this minus sign. So, value BEV from this relation after putting value will become BCV equal to 0.0043 mho. So, total susceptance for the voltage regulation at this BCV plus BPF will be 0.0433 mho, and total value of the capacitor for this voltage regulation is CT equal to BT upon omega, that comes 141.00 microfarad. So, this if you put this much capacitance in parallel to this load, you will get a same voltage across the load what it is the source voltage, and this will be the condition for your 0 voltage regulation like So, kVA rating if you have to find out for this compensator, that will be V square BT, and you can keep the value of V square 220 into your B 0.0443, and it comes 2.1441 kVAr. That much capacitor if you connect it, then you will get a 0 voltage regulation, and the voltage drop across the source impedance after the compensation we can find out Is nu into Zs, and that Is nu will be is nothing but you can call it VL into your typically now GL plus JBV. This is that equivalent, you can call it the your admittance of the load plus compensator. Okay. So, that will be virtually the current multiplied the source impedance, that is Zs. So, if we keep the value of it, now the drop in the source impedance will be 35.29. In spite of this drop, we will get the voltage across the load typically of order of the same as your 220 volt like also. So, that is typically the voltage regulation problem. Now, we come to the third another problem. We have all the variety of the problems you can think about here. So, you say another problem here, a single phase AC supply has the AC mains voltage of 220 at 50 hertz and the feeders or source impedance of 3 ohm, inductive reactance after which a impedance of 12.09 ohm is connected. Calculate the voltage drop across the source impedance, voltage drop across the load with series compensator, and if this series compensator is lossless element is used to raise the voltage across the load same voltage, calculate the voltage and kVAr rating like Well, in this case we will be connecting compensator in series with the source impedance after which the load is connected, and you can see the typically waveform for both the cases for power factor correction and typically for voltage regulation both the cases. Well, we can have a solution here, given that supply voltage of 220 Vs equal to 220 volt, frequency of supply of 50 hertz and single phase load ZL equal to 12 plus J 9 ohm, the source impedance is Zs equal to Js 3 ohm, the total impedance of load is ZT equal to ZS plus JL, that is 12.12 ohm is 16.971 ohm, and load current before compensation is as a old current Vs upon ZT 220 divided by 16.971 equal to 12.96 ampere. The voltage drop across the source impedance before the compensation is Vs Z equal to Is old into Zs, that is 38.89, and the voltage across the load after the before the compensation is V load equal to I old Zs 194.45. So, voltage across the load reduces because of the drop in source impedance, and is a power factor of the load is lagging nature. So, certainly you will have a poor voltage regulation. So, since after the compensation you desire to maintain unity power factor at AC mains, then the load current is Is equal to Vs upon RL, that is 18.33 ampere, and voltage across the source impedance will be Zs into Is into nu into Zs. So, that will be you can call it 18.33 into 3, that comes 55 volt, and the voltage across the load will be your VL equal to Is ZL. So, 18.33 into 15, it becomes 275 volt. So, you can understand here. Now, we put a series compensator, that is the reason the voltage have gone more than typically of your 220, that has become 275. Since the circuit is an inductive circuit, therefore, the compensator have to be capacitive in nature, and the net reactance of the circuit is same as the compensator or capacitive reactance like. Therefore, the net capacitive reactance is Xc equal to XL, XS plus XL, and that is typically you can call it 3 plus 9 ohm equal to 12 ohm, and the value of the capacitor for power factor correction is your C equal to 1 upon Xc into omega. It comes to 65.26 microfarad. So, net kVA rating of the compensator in series Is square Xc, it comes 18.33 into 12, it comes like a 4033.33 VA equal to 4.033 kVA. So, since it has increased the voltage across the load higher than the supply voltage, for which normally the load are not designed, therefore, such passive series compensation is not used in practice in distribution system. So, this series compensator is also used to raise the voltage. I mean, that is a second another part of this numerical. The series compensator is used to raise the voltage across the load to same as the input voltage, and then we have to find out the compensator element. So, that is the value of the voltage regulation is Xcv equal to minus Xs equal to minus 3. So, C will be equal to 1 upon Xcv into omega. So, that is 1061 microfarad. I mean, what we are doing here, why putting this capacitor equal to source impedance, because we have to only compensate here the drop of the source impedance. So, kVA rating of the compensator rating here for voltage regulation is X Q equal to I square Xcv, that is 220 divided by typically 15 ohm square into 3, and it comes 645.33 VA, and it comes 0.645 kVA. So, you can call it like a typically this compensator rating for voltage regulation is much lower than what we got in shunt compensator. So, now from this previous problem and this problem we can conclude two things, that I mean the series compensation is not good for certainly for power factor correction, because voltage across the load increases much more what the load can have it, but for the voltage regulation across the load to be rated, the kVA rating of the voltage regulator here is much lower. So, that is the reason you might see in the transmission system we use the series capacitor, because that becomes the more effective as far as voltage regulation is concerned, but in you can call it distribution system we always use the shunt compensation. So, that you can interpret from these two numerical by comparing the rating of these compensators like. Coming to now the numerical problems on 3-phase 3-wire system. A 3-phase 3-wire shunt compensator consisting of lossless passive elements is employed at 415 volt 50 hertz distribution system to provide load balancing and power factor correction of a single phase load of 15 kilowatt unity power factor connected between two lines as shown in the figure. Calculate the supply line current, compensator current, the value of compensator element in farad or Henry, and its kVA rating. So, what we can do here the load compensation, which is a very interesting classical problem, because such load are connected line to line like a traction system, or it is even a furnaces, we use such kind of load. So, providing the compensation for here, I mean making this load a unity power factor supply system of 3 wire system by lossless element of these two elements. You can see just like the after calculation these value are put, and you can see I mean the 3 phase supply current, balance current, and the compensator current is also given below, and load current and load voltage is also given in this waveform. So, based on that we have a now the solution to this problem, given that the supply voltage Vs equal to 415 volt, frequency of supply 50 hertz, and single phase load of 15 kilowatt at unity power factor connected between two lines to be compensated as a balance load on the 3 phase system. After the compensation, this load relies as a balanced 3 phase unity power factor load. So, therefore, the supply line current are as the power consumed by the load, that is 15 kilowatt or 15,000 watt, divided into root 3 into 415. Why we are taking root 3? Because it is a line voltage. So, it become 3 times the phase voltage. If we take a phase voltage 415 by root 3, so it is a 3 times phase voltage. So, that becomes the line current. So, it becomes 20.868 ampere, and all 3 phase currents will be the same magnitude, you can call it, in because it is a balance. Now, load balancing is there at unity power factor. So, that is the equivalent load current like here, and for such a load compensation the real admittance of the load, which is 15,000 watt divided by 415 square, because load is connected across the line to line. So, you can call it as a single phase load connected across the 415 volt. So, you get the conductance of it 0.087 mho has to be complemented with reactive admittance network across the other two lines to obtain result balance load on the AC supply. And this problem has been investigated originally by Schumann at the beginning of 20th century. It can be easily shown that the load on the AC supply becomes balanced and remains real if capacitor susceptance C BC, the value of GLAB divided by root 3 is connected between phase B and C, and the inductive susceptance BCCA, that is minus GLAB divided by root 3 is connected between phases C and A. And putting the value of this, I mean we can get the value of IC compensator across the BC equal to ICA, I mean both are equal in magnitude, VLL line voltage into GLAB divided by root 3, that is 415 into 0.0500. So, it comes like a current comes only 20.86 ampere. Therefore, the BCB, the value of element GLAB by root 3 is 0.0528 mho, and the capacitance equivalent to is BCB divided by omega, it comes 160.06 microfarad, and the another compensator which is inductive across the another line, two line, that is CA line, because load is connected across AB. So, it will be GLAB divided by root 3 and minus 0.05028 mho, and the inductance of this LCCA will be 1 upon omega BCCA, that is 63.30 millihenry. And this will convert the whole network into 3 phase balance supply system, and you can find out the kV rating of the compensator element will be QC BC and equal to QCB CA equal to Q V square GL upon root 3, and it comes 8660.254 VA, or you can call it equivalent to 8.66 kVA. That is the compensator elements, I mean rating of one element, similar rating of another element also to be connected across the another line like. So, that is we demonstrated that how a single line to line resistive load can be made equivalent balanced sinusoidal unity power factor load using the lossless element, only means inductor and capacitors like I mean also. Coming to typically another 3 phase 3 wire shunt compensator consisting of lossless passive element is employed at 415 volt 50 hertz system to provide load balancing and power factor correction of a single phase load of 25 kVA at 0.8 lagging power factor connected between the two lines. Calculate the supply line current, compensator current, the VA value of the compensator elements farad and Henry, and its kVA rating. Well, you can call it now compared to previous one, I mean we have to connect another compensator for power factor correction and make it the line to line load of line AB of equivalent to a resistive load, and then remaining element comes in the similar manner as we did in the previous numerical problem, and these are after putting compensation the real waveform of this numerical problem you can see, and current all 3 phase currents or line currents are in phase with the voltage like and you can see the all voltage and current of the compensator like also. So, coming to the solution of this, given that the supply line voltage is 415 volt frequency of supply 50 hertz and single phase load of 25 kV at 0.8 lagging power factor connected between the two lines, it will be compensated as a balance load on the 3 phase distribution system. So, after the compensation this load is realized as a balanced 3 phase unity power factor load. Therefore, line current will be ISA equal to we have to calculate the power. So, it is 25 kV at 0.8 power factor. So, that real power will be 25,000 into 0.8 divided by root 3 into 415. So, current comes 27.824 and these balance current of unity power factor will flow in all the 3 phases, and for such a load compensation the real admittance we can find out from this real power 25,000 into 0.8 divided by 415 square. So, it comes 0.116 mho had to be complemented with the reactive admittance network across the two other lines to obtain the resultant balance load on the supply. It may be simply derived that the load on the AC supply becomes balanced and remain real if capacitive susceptance of BC equal to GL AB by root 3 is connected between the line PBC and a inductive susceptance of BCGA minus GL AB divided by root 3 is connected between the phases C and A. Therefore, the compensator currents are as ICAB equal to QL AB divided by V, and that is 25,000 to typically 0.6, that will be a reactive power divided by 415. So, it is a 15,000 by 415 and equal to 36.14 ampere. Similarly, ICB will be again Vs GLB by root 3. So, again this current is 27.82. So, therefore, the BC will be GLA by root 3. So, that is 0.067 mho and CBC BC by omega, it comes to 213.41 microfarad, and BCCA GL by AB by root 3. So, it comes around 0.067 mho and LLC will be 1 upon omega BCA, that comes 47.5 millihenry. So, moreover, for power factor correction at line AB across the line AB such as QLAB equal to QCB equal to 25,000 into 0.6, that is a reactive power, and capacitance equivalent will be, because it is a single phase circuit, so QCAB V square omega, and this comes to 27.23 microwatt. So, KVA rating of capacitor element you can find out across the AB, that was typically of 15 KVA, and QCB and QCB other two will be B square GL upon root 3, that will be 11.54. So, after putting these three compensator, we will get a unity power factor sinusoidal balance current in the net compensated load like.